reduce this to broadband shock noise, the flight effects, although I will incorporate studies.
All right, well, that sounds great, okay. Cool.
Yeah, I selected this topic because of our honored person. He worked on broadband shock noise. He made big contributions to the acoustic analogy. He did, I learned his PhD thesis was on jet noise. So I thought I use this occasion to say something about against the recent papers which said acoustic analogy is no good because it fails to explain so many features. And I will show that the acoustic analogy explains almost all features of jet noise you can find if you do it right. The broadband shock noise itself has gained renewed interest, as we have seen. Military aircraft noise, the jet engines become better and better, and all the efficiency increases are changed into jet speed rather than bypass ratio on military engines. So we have very high jet speeds, very high temperatures. So broadband shock noise is an issue there, and it is believed that broadband shock noise is also important for cabin noise in the rear cabin, although this is not somehow verified. The content of this presentation is that I will show that broadband shock noise can be developed with the acoustic analogy, with a very simple turbulence model. And I will compare these results with new experimental data which became available last year. This is some figures from this paper. You see this immense increase in the forward arc. This is 30, 40, 50, 60, 70, 80, 90, 100, 110 degree relative to the flight direction. And this peak is avoidable. If this can be cut off, you get a substantial reduction of noise emission in the forward arc. And it isn't even found in these tests that the OSPL in the forward arc is larger than the rear arc. So jet mixing noise is negligible in comparison to this. So now I want to present how you can do this with the acoustic analogy. The first thing is that you have to study everything in a nozzle fixed coordinate system, not in the moving eddy system. In the nozzle fixed coordinate system, this was always done by Michel in his papers between 1970 and 1983. Because the reason is, in this coordinate system, all these turbulence values are stationary random. You can make long averages, and the mathematics are correct. And this system was first used by Ridner in 1959, and he came to the conclusion that the results between this coordinate system and the other coordinate system are identical, but he did only look at the convective amplification. So he did not realize that if you look at the frequencies, you get completely different results with both assumptions. If you assume a coordinate system fixed on the moving eddy, it moves backwards to the rear, then the frequencies in the rear arc should be higher than the forward arc, of course, due to Doppler frequency shift. And this is true for the static case as well in flight. Even in flight, the eddies move to the rear. There is no single experimental verification for this. The experimental evidence is that the frequency spectrum is almost constant at subsonic jet speeds in angle 0 to 120 degrees. Only in the very rear arc we get the frequencies go down, not up. But this is due to reflection effects. And we find in experimental data that the frequency spectrum in flight is Doppler shifted according to the flight Mach number. So every indication, experimental indication, is that the sources have to be discussed in a coordinate system that moves with the nozzle, with the aircraft. And the following theory is then based on such a coordinate system. You have to use the convective wave equation, convective light field equation here in terms of the pressure, and the source on the right-hand side is then given by this. This is completely exact. There's no assumptions made. Only the normal Navier-Stokes equations have to be valid. So if it simplifies, if heat conduction and viscous dissipation are neglected, so in that case we get two terms. One term is the normal quadrupole noise source. This leads to the well-known U to the 8th law. And the second term are dipole sources. And you can see that because it's only there if the density is not identical on both sides of the shear layer, that these dipole sources only occur with heated jets or cold jets or whatever. So we have two sources. And the interesting thing is the dipole sources lead to a U to the 6th law. And we just had tests shown that we have U to the 6.5 at 90 degrees. So you find at 90 degrees at almost all engine jets with modeled bypass ratios, you find a U to the 6th law. So this could be that this noise source term is very important, and we always neglect this in our discussions. This equation, this convective wave equation, has a very simple solution, a very compact computation, if you describe the results not in terms. This is a wind tunnel situation, nozzle fixed. So not in terms of the angle theta relative to the nozzle or to the source and the distance from the source, but in terms of the wave normal distance and in terms of the wave normal angle. So all my results I will show are in terms of this distance, or the distance doesn't appear, but in terms of this angle. So while the sound propagates in this direction, it is convected downstream by the external flow. So, and with this assumption, we get the power spectral density of the far field sound. Now I talk only about the quadrupole sources, which is a double integral. A double integral, this is in the acoustic far field, but in the geometric near field still. We see here the distance, the wave normal distance, the Doppler factor to the third. Second integral, the same quantities, but for the second volume element. This is the cross-spectral density of the sources. And this is a phase difference due to the retarded time differences. So the source quantity is given here. They are known, second time derivative of this term here, rho u square in the direction of the observer, in the wave normal direction. The retarded time direction difference is given by that. So where does the motion come in? Of course, the sources still move. We cannot assume that they are stationary. They still move, but they are considered in the cross-spectral density of, here I've repeated this equation, and now I look at this cross-spectral density, the cross-spectral density between position of the outer source volume element and the position of the inner source volume element, and function of frequency, of course. And this cross-spectral density has a magnitude and a phase, and the motion is in this phase. The phase is given by first simplification I now introduce is that the phase difference is determined only by the axial separation in the axial direction, and divided by the phase speed. The phase speed, this is the convection speed we saw in the previous talk. The phase speed is a function of frequency in stability theory. It can be as low as 0.2 times jet speed for very low frequencies, and it can be as high as 0.8 times the phase jet speed. But I assume in my calculations now that it is 0.7 times the jet speed. So the phase is given directly as a function of axial distance between these two source elements. And then you can, the absolute value of the cross-spectral density, you can expect in terms of the power spectral density, one source position times power spectral density, second source position times coherence gamma. And the coherence gamma we don't know. We know the phase difference due to motion, we know the phase difference due to retarded time differences, but we do not know how the coherence decays when the distance between the two source volume elements increases. So I repeat this once more in an abbreviated form. The inner integral is replaced by Fq. I now assume I'm in the geometric far field of this inner volume. And if I then, in addition, assume that the source strength, these two power spectral densities, remain constant inside the inner volume, then I get a simple expression like this here. This is the coherence, which is a function of axial separation. This is the phase difference due to source motion. And this is the phase difference due to the retarded time differences. So this, I will, in the following, only study this integral. So that is the source, the radiation due to one source element. And again, this equation for one source element, and now I assume very drastic assumption. I really use a very, very simple model. I assume that the radial extension is negligible of a jet. So the jet collapses to that one line. And in that case, the retarded time difference between two source positions is described by this expression. So the phase difference here is then k, that's the acoustic wave number, times a length scale, an axial length scale of the turbulence, times the inverse of the phase Mach number, and this is the cosine of the emission angle divided by the Doppler factor. And this C is a relative length separation. The axial separation is normalized with the length scale. So now, what coherence model should we use? Normally, if you make numerical computations, CFD computations, and you have a length scale, you assume that the length scale follows this e to the minus c squared. So this is a normal assumption if you sit on a moving eddy. But we are not sitting on a moving eddy. We are located on one position and compare with the second position. The turbulence moves by and degenerates. And recent experimental data presented in Manchester, and I couldn't locate this paper again shortly before I left. So I do not know the name. Maybe some of you can help me. Recent data suggests that the coherence decays like e to the minus separation. So we have two completely different coherence models which can be used for further analysis. Both models have a closed form solution, and in the first model, this integral Fq, the nominal sound of one source element, is given by this equation. And for the second model, the contribution of one model is given by this expression. And now I'm going to evaluate this data. I have no directivity of sources, uniform directivity of the source, no assumption so far, only interference. So with the coherence model 1, we'll get directivity with jet model, source model 1. Now with the Struer number, frequency times coherence length scale divided by jet speed equal to 1, we get this expression, this relation here. Looks very much what you measure. You get the peak radiation where the Mach wave radiation occurs here for this Mach number 1.8. I assume relative phase speed of 0.7 in this case. And for small Mach numbers, you get a small variation between front and aft. And for high Mach number, you get a large one. And this in 0 dB is the maximum you can achieve. So if you increase further your jet speed, it will never increase. So that is one explanation that the efficiency of jet goes down at high speeds. You cannot get more than 1 out of this inner integral. And interesting, now a comparison between this source model and the other one. This is the source model 2, and you see that the source model you introduce makes a big difference. In this case, we have now about 20 dB between maximum and minimum, and here we get 35 dB. So here, the kind of source model you introduce has a big influence on the radiation efficiency as a function of angle. So, but you can deduce that the interference alone explains directivity. Now, a study of the coherence length scale on the directivity. The Struer number is defined here with the coherence length scale, and if you increase the length scale, the directivity I'm not sure about this. If I have not reversed this, sorry, I have to check. But the length scale has a dramatic influence on, I think it's the other way around. But nevertheless, so the coherence length scale has a dramatic influence. In this model, the variation, the influence on the directivity itself is not very big, but in this model, the influence on the directivity is very heavy. And so you can determine from the directivity, from the shape of the directivity, you can determine the length scale. Now the flight effect. So these previous results were without flight effect, now with flight effect. And you see a very interesting result. Coherence model 1 gives a strong forward arc amplification, and the coherence model 2, almost no coherence of forward arc amplification. So in this case, the Mach number is not 1.4, the acoustic Mach number, which is relatively low, but this is, and Mach 0.8 would be a cruise Mach number of an aircraft. So in this case, we would, if this coherence model would be right, then we would have very high radiation forward. So in the aft cabin, if you measure outside, you would measure what is coming from the jet way behind the aircraft. So that would be an explanation why we have such loud jet noise in the rear cabin. So it would be jet mixing noise, not broadband shock noise. But the coherence model 2 is the opposite. So we really don't know. I would have to look now if there is a closed form solution for an intermediate model. Now broadband shock noise. That was the topic of our talk. The broadband shock noise is generated by the almost periodic flow field in a jet. And a circular jet, or the pressure distribution, the mean pressure distribution in the circular jet with shock cells can be expressed in terms of a series expansion, which is not a Fourier series expansion for a round jet. So you have axial wave numbers, which 1 until infinity, and you have amplitudes. And okay. These, the wave numbers here are of course important, and the wave numbers for this, Ulf Michel has developed a closed form solution which includes the influence of light Mach number. You see the wave numbers decrease as a function with increasing Mach number. So now broadband shock noise, we need the sources for broadband shock noise. And I now assume that the sources are modulated. So the velocity fluctuations in the jet are modulated according to the shock cells, which is experimentally proven by Jack 20 years ago. So at least there is a paper where you measured the velocity fluctuations as a function of shock cell space location, and there is a big change in velocity fluctuation level across the shocks, across the cells. And so I assume that the sources, the turbulence sources which I used before in my calculation are unchanged, except that they are now modulated. And the modulation amplitudes is En, and En is then an arbitrary amplitude times e to the alpha n axial separation plus minus alpha n axial. So the axial separation plays a role, and the axial wave number plays a role. And then the source cross-spectral density is then given by the original source cross-spectral density 1 plus a double sum over this term. And if we evaluate this, we get this result here. We get a new cross-spectral density times the phase difference due to retarded time differences. This are the power spectral density in source position 1, and power spectral density in source position 2, interference, where we have to introduce some of one of the two models, times e to the minus these two phase difference, source motion, retarded time difference. And now we get additional terms. This first line here, or second line, has as an argument y the axial separation y, which means that the source itself changes with angle. So the contribution of jet mixing noise changes. Of course, if the fluctuation level is large, then it goes up. If the fluctuation level goes down, then the source strength goes down. But in the average, this contribution should be 0, because increase on one position in the shock is compensated by a decrease in another position. But interesting are these two lines. Here we get an exponential factor times an exponential function of the axial separation. And so if we combine this function with this function, we get a new interference function. And the new interference function is broadband shock noise. The new interference function is now these two terms we already knew, plus minus this term. This is the example for the first wave number, which determines the lowest frequency of broadband shock noise. And like in the previous result, we get maximum radiation when this angle is 0. And in normal jet noise, mixing noise, maximum radiation occurs at the Mach angle. Then for the Mach angle, this phase angle is 0. But but here with this additional term, we get also phase 0, and we get a new kind of Mach wave radiation. And this is described by this. So a Mach wave radiation occurs, and this Mach wave radiation is broadband shock noise. And we can determine the frequencies from these equations with this very, very simple turbulence model, that the peak frequencies in a nozzle fixed coordinate system are given by this. This is the axial wave number, this is the phase speed, this is the Doppler factor, and this is some Doppler factor that, okay, this is the equation. And the peak frequencies in the flyover coordinate system, that is when we measure on the ground and the aircraft comes by, flies over, is then given by this equation. And this equation is not identical to the equation Tam gives, but then if you look carefully what is the difference, you find out Tam uses the position, the angle at reception time, not the, when it measures the aircraft, but the emitted sound is somewhere else. So if you replace this angle by this emission, not the emission, the observation angle, then the frequency of the scaling, or this equation is identical. And if you set UF, or the flight Mach number to 0, you arrive at the same equation that was derived by Ffowcs, Williams, and Kempton, and by Harper, Bohn, and Fisher. So the equations are, the frequencies are the same, but they are derived in a completely different way. So now I study the ratio. I can now determine a ratio how the frequency changes with angle. So this is the peak frequency in the flyover coordinate system. And if I compare the peak frequencies at any angle with the peak frequency at 90 degrees, I get this relation. And this here is a comparison with the measurements I showed you in the beginning with the norm. This is just one of the many cases they have. In blue are the measurements, the peak frequencies I derived from these tiny figures, so they can be a little bit wrong. And this is the calculation on approximation by this equation, and you see the experimental flyover frequencies are perfectly described by this frequency relationship, which is derived with a very, very, very simple turbulence model, just a linear jet. So, and this is the emission angle. You see the emission, and this is the frequency on the ground. This is the frequency seen on the aircraft. So, if you want to see broadband shock noise on the cabin, then this frequency noise is important. Or if you want to find out the influence of broadband shock noise to acoustic fatigue, then this is important. And if you extend this to the emission angle 0, maybe here, then you get the frequency which goes directly to the nozzle and which could generate screech. So the screech frequency is the same frequency as 0 degree. So now I want to show that in principle you can derive many unknowns from just one flyover. So the frequency, the peak frequency is given in the flyover system is given by this equation, and this cosine can be described in terms of the observation angle cosine theta with this equation. So you can only see the aircraft, and you can only measure during the flyover this angle, and then you have first to calculate the emission angle and then calculate the frequency. And we have 4 unknowns in this equation: the phase speed of the disturbances in the flow, the flight speed, the speed of sound at the aircraft altitude, which is not necessary, no, but you have a good idea of where it is here, and the first wave number of shock cell spacing. So 4 unknowns. And since during the flyover you make measurements at many angles, in principle, you can determine all constants from just one flyover measurement at 4 different angles. If you take more angles, you can make a least square fit, and this is what I've done. The example here in this previous figure is wave number is 11.1 per meter. Okay. So, and then you can also determine the coherence length scale. The relation between this integral in comparison to the integral at the peak frequency is given by this equation, and the only now unknown is the length scale. So from one flyover, you can determine the turbulence length scale in the jet. So conclusions: broadband shock noise can be described with the acoustic analogy. The coordinate system has to be attached to the nozzle, however. The source term has to be modulated according to the axial wave numbers of the shock cells. Frequency scaling laws agree with previous theories, and following data can be determined from one flyover. Thank you very much.
Perhaps we have time for one question.
I think I just want to make a comment, which is we're going back to 50 years ago. What has found all these final side effects are making true, repeating similar things what they said 40 or 45 years ago. And so I just want to make a comment on that more, which is revisited again as what we've been confused for 40 years using our models, but I don't want to go through all that.
It's important to be confused, though. Keep us a fuel alive. Thanks.
Could I make a comment?
Yeah.
Okay.
Listening to that, I found most interesting. And it reminded me very much of listening to lectures by the late Professor
Michel?
No,
No.
Michel, yeah. I found in listening to his lectures that I tended to disagree intuitively with many things he was saying.
I know.
And I enjoyed very much the fact that he tended to disagree with everything I said as well. But nearly always, when you looked around it, it came out to the same result from different points of view. I thought it was very, very interesting. Now, he put in a lot of emphasis on stability theory.
Yeah.
And stability theory is usually linear, a small amplitude theory, to do with things to do with turbulence and turbulence production. And I naturally tend to disagree with that as well. But as I said, in the end, it comes back to having much that is very satisfying in the explanation. And at one stage, there was a meeting in Brussels a long time ago that I was organising, and I wanted to be a little provocative about the lectures, and I insisted on telling people, the people whose opinion I wanted most on certain aspects, what the title of their lecture was. Come along to this lecture, give an invited lecture, your title will be this. Because I wanted their opinion on a certain, that to make it a good meeting. And I remember telling Crichton that he was going to give an invited lecture, but please, it'll be on the title of what has instability theory to do with turbulent eddies. And I think that much of the blame for the way the people have been given titles might originate from that.
Well,
that explains it.
the only thing that I take from instability theory is that the phase speed of the turbulence fluctuations is a function of frequency. So you have to be careful. And so when you measure in experiment that you get changes in frequency spectra, it could be that it is a function that the axial length scale changes or the phase speed changes with frequency.